have the honor and the pleasure to present to you today my work, which is related to the theoretical study of structural, electronic, and magnetic properties of full Hassler compounds. So after the motivation, I will present the different types of Hassler. In the third part, I will present the calculation method, and in the fourth part, I will discuss the result of my calculations, and finally, I complete my work. The Hassler alloys are generally a system of stoichiometric composition with the general formula XYZ. In this class, X and Y represent transition metals, and Z is an element of column 3, 4, and 5. They have experienced an increased and recent year, both of their possible application in the field of spintronics, especially as magnetoresistance and tunnel magnetoresistance devices. Most of these materials are semi-metallic and magnetic, in particular. The case of ferromagnetic, hence the name by half ferromagnetic metals. The figure in the slide represents an overview of the possible combinations of elements forming this kind of materials. Hassler alloys are ternary compounds that are divided into large families. We present here the first one. Full Hassler alloys are characterized by the chemical formula X2YZ, of which X and Y are the transition metals, and Z is an element of the group 3 or 4. Of our materials, the calculation are performed using the density functional theory DFT for work in the full potential linearized augmented plane wave method, as implemented in the via-2 package. The exchange correlation potential was treated using the generalized gradient approximation GGA in the PBE parameterizations and the MBG approximation. The results obtained for the values of lattice parameter compressibility modulus between the ferromagnetic state and the non-magnetic state in the two mercury and the copper types of the alloy studied are grouped together in Table 1. The results are in good agreement and show that the total energies obtained in the magnetic phases for these structures are lower than the non-magnetic phases in the same type of structure, which confirms that all the type of alloys studied are stable in magnetic phase. The calculation of the electronic density makes it possible to understand the band structure and its origin. For the chrome aluminum alloys, the density of spin polarized state is studied at zero pressure and room temperature. The total and the partial density spectra of the state of the two compounds show that the alloys accept metallic behavior for the minority state and the superconductor behavior for the majority spin state for the both GGA and the DGA-MBG approximations around the Fermi level. You can see this behavior clearly in the figure 2. The asymmetric density of state for the spin up and the spin down states clearly indicates that the alloy study is a magnetic material, and it's clear that both compounds accept a semi-metallic character. The total magnetic moment of our compound with the atoms at the optimized lattice parameters are shown in Table 2. The total magnetic moment is about 3 microbar for the complete Hassler for both GGA and GGA-MBG approximations. The study of the properties is carried out by the linearized fully potential augmented plane wave method as a part of the DFT density functional theory implemented in the via-2 computer board. The optimization of the structure shows that the copper magnesium aluminum type in the ferromagnetic case has the most stable electronic properties such as band structure and density state. Results of the band structure obtained clearly show a symmetric behavior. The magnetic moment calculated for the GGA and the MBG approximations are about 2 microbar complete or with good agreement with the role of center bowing.